Let's learn about how to calculate the arc length of a curve. Before doing this, we first need to recall the Pythagorean theorem. The Pythagorean theorem relates the three sides of a triangle. So let's say we label the longest side C, the hypotenuse is C, and we put the bottom to be A, and we have the uh, right side to be B. Then the Pythagorean theorem says that C squared is equal to A squared plus B squared, right? So what I want to do now is I want to label the two corners of the right triangle that are opposite the corner that has the right angle. So I'll call one of the points x1, y1, and I'll call the other point x2, y2 like this. And I just want to use the Pythagorean theorem to express the length of this side C in terms of x1 and x2 and y1 and y2. Okay, so what we can see is that A, the length, that distance A is just going to be x2 minus x1. And I'm going to square that. And we can see that the length B is just going to be the difference of the y values. So it'll be y2 minus y1 squared. And if C is the length that I want, I can just simply put C and then take the square root of both sides and get C is equal to the square root of that expression that I just wrote earlier. So and this is really going to help us answer our question of finding the arc length. Okay, so we want to use the Pythagorean theorem to calculate the length of a line segment. Now, what line segment do we want to calculate? Well, our goal in this section is to calculate the length of this red curve over here. And this red curve is going to be given by the function y is equal to f of x. And we want to calculate the length of this curve as the x values range from a to b. Okay, so we have a curve that looks like this, and the starting point of the curve is x equal to a, and the end point of the curve is x equal to b. And what we're going to do is we are going to approximate the arc length by calculating the sum of the length of line segments. So what you'll see up above here is that we actually have 9 line segments. Here's one line segment, here's a second line segment, here's a third, the fourth, the fifth, the sixth, the seventh, the eighth, and the ninth. Okay, that 9 number isn't important. The point is that if we use these blue line segments and we added them all up, that would be a good approximation of the arc length. So this is what we're going to do. So we're going to say the arc length of f of x from A to B, this is going to be approximately equal to the sum as we count the number of line segments going from 1 to 9. And then I'm going to represent the arc length of a particular line segment with absolute value signs. And it's going to be absolute value of pi1, pi. I'll put a little line over the top to indicate the line segment. And then that's sort of these absolute value symbols sort of indicate that we're finding the length of this line segment. Okay, so let me label that. I'll mention that, this part right here, this is the length of the line segment from pi minus 1 to pi. That earlier picture up above dealt with 9 line segments. Instead of looking at 9 line segments, let's generalize the line segments. Okay, so if we look at this picture is just supposed to be an abstract diagram, and we're taking n line segments instead of 9 line segments. So uh, if we were to write the formula for what this guy looks like, this approximation looks something like the sum. This time we're going to go from 1 to n, and we still have the same idea. This is pi minus 1, pi, that's what we call each line segment, and we're going to put a line over the top to indicate we're talking about a line segment. And the absolute value lines are indicating it's the length, okay? So what we want is, we really, want a formula for this. Okay, and we use our Pythagorean Theorem formula to get it. So we could say that the length of the line segment from pi minus 1 to pi, that length is going to be equal to, as we had saw earlier with the Pythagorean Theorem, the square root of xi minus 1 squared plus yi minus 1 quantity squared. Okay, and really we could rewrite it like this. We could really rewrite it as delta x squared plus delta y squared, all under one giant square root. This delta notation we've seen before. This is the change in x. And delta y would be the change in y. Okay, so we're kind of measuring these lengths here. We're thinking of the length as the change in the x coordinate, and the length here as the change in the y coordinate. Okay, so what's our plan? Our plan is to use what I call the basic calculus idea. And this is how we found the area under a curve with a definite integral. We use this idea in calculus all the time. What is this basic calculus idea? This basic calculus idea is the following. First, we're going to approximate the arc length with n line segments. When we worked with Riemann sums, we approximated area. Now we're using line segments. The next thing we're going to do after we create this approximation is we're going to take a limit. And in doing so, we're going to end up with an integral. So we behold and wonder in awe at the amazing integral that we have left to evaluate. I'm going to continue this in a subsequent video. I don't want this video to get too long, so let's watch the next part on a second video. Okay? Take care, everyone.